Okay, in this video, I'm going to discuss various types of parameters in structural equation models. During model specification, you must make decisions about how to treat your parameters. Specifically, you must decide on what parameters should be freely estimated, that is, free parameters, what parameters should be fixed at a particular value, those are called fixed parameters, and or whether certain sets of parameters should have constraints placed on them in terms of their estimation, and these are called constrained parameters. The choices you make regarding how to treat individual parameters within a model will impact your understanding of the relationships among variables within and between populations and will play a role in achieving model identification. So all examples in this demonstration use a basic multiple regression model, although the concepts apply to all forms of models you could theoretically run using SEM. Also, the demonstrations here are based on a covariance matrix from an example in Chapter 5 of Schumacher and Lomax in their 2016 text. The matrix summary did not contain means, so although the examples here involve tests of path coefficients and variances, the concepts are also applicable when testing means and intercepts in SEM. So here we have an example of a multiple regression model specified in AMOS. So we have basically we have age and we have years serving as predictors of a variable deference. And deference within the model is referred to as an endogenous variable because we have predictors of that variable. And age and years are considered exogenous, meaning that they don't have any predictors pointing to them. We do have a double-headed arrow between them that signifies that we're talking about a covariance between the two. So here we have the same model after naming all the free parameters. So in AMOS, you can actually name the parameters if you want, and I'll show you how to do that. But basically, this particular model right here, you can see that these are all the parameters that are being estimated. So we have three variables that are included in the model, but we're estimating an error variance, we're estimating path A, path B, we're estimating the variance for age, the variance for years, and then also the covariance between our age and years variable. So these are called free parameters. These are being estimated by the program. And you'll notice too that we have a 1 on this path right here, and this is essentially what's called a fixed parameter. In other words, we are fixing the relationship between error variance and deference. That path coefficient is being fixed to 1, and this is typically used or generally used when working with latent variables in SEM, so that we can scale those latent variables in relationship to various indicator or manifest variables. So we have in this particular model then we have two types of parameters. We have free parameters that are being estimated, and then we have a fixed parameter that is essentially fixed to a given value. So let's open up AMOS and take a look. And before I do that, I want to show you this is the matrix summary data that I was telling you about. And we'll go in here and open up our program with AMOS containing our model. So I haven't named the parameters, but if I want to name them, I can easily do that by just right-clicking on any of the objects and go to Object Properties, and then you can assign a name. So let's say I go to Object Properties after right-clicking on the error term. If I go to Parameters, you can see where it says Variance. So you'll notice that there's an empty space, and that means that you're estimating the variance for the errors. But if I want to name that and still have a free estimation of that, I can just name it error variance or whatever I want to type in there. Now this parameter right here is fixed at 1. So there you go. Now if I want to name these path coefficients like path A and path B, I can click on this and I can type in path A and then path B. Now I'm not getting to it yet, but if I name these two paths, provide the same name for those, it will actually yield a constrained estimation of those parameters, and I don't want to do that. So make sure that if you're trying to uniquely estimate the parameters in your model, that in AMOS, that you make sure that you have named each element or each parameter separately. And for age right here, the variance, I could call this variance 1, and then this right here, variance 2. And then the covariance between them, I could just type in covariance here. So the naming's arbitrary. Most of the time, I don't generally go about naming the individual parameters, but this is just to highlight in this in these demonstrations, the parameters that are free versus fixed. So at any rate, now when I click out of this, I've already, I've got my data imported into the program. So also under analysis properties, under output, one of the things I'm asking for are the residual moments, and I'll kind of talk a little bit about that shortly. But I'm going to go ahead and estimate the model. And you'll notice when I hit this little button right here, these are all the free parameters that have been estimated. So you'll see that we have the variance for the errors. We have, again, this is the fixed parameter right here, so that remains 1. We have a freely estimated path coefficient here and here. We have the variance for age, the variance for years, and then the covariance between the two. You'll notice too over here where it says chi-square is 0 and it's got degrees of freedom is 0. So when your degrees of freedom is 0, you have what is called a just identified model. So basically what that means is that the number of unique elements within the sample variance covariance matrix is equal to the number of free parameters that are being estimated. So we had three variables in our model. So we have essentially 6 elements within the variance covariance matrix. We just would say the basic formula for the number of elements within the variance covariance matrix is P times P plus 1. That's the number of variables plus 1. Divide that by 2. And so you can see right here that we have 3 variables, so it's 3 times 4 divided by 2. That's going to get us 6. So the number of freely estimated parameters is 1, 2, 3, 4, 5, and 6. So that's why when we subtract the number of free parameters or parameters being estimated from the number of unique elements within the variance covariance matrix, we get a degrees of freedom set at, or degrees of freedom equal to 0. So you can see, looking at our output, I'll also show you that, which if we go under estimates, you can see that we have, we've basically attached labels to the parameters, but all of these are freely estimated. You have your significance test. There's the covariance right there, the variances for age, years, and the error variance. And like I said, you don't have to name them. I generally don't bother naming the parameters in most cases, but this is just to highlight, which parameters are being estimated versus which would be treated as fixed or constrained. So in theory, we could fix other parameters within the model to certain values. So in this particular demonstration, I'm going to fix the path coefficient from age to deference to 0.22. So this doesn't make necessarily sense from a theoretical standpoint, but this is just to highlight the difference between a fixed and free parameter. So I'm going to click back over here, and where it says path A, I'm going to right click, go to object properties, go to parameters. Actually, you got to make sure you get it right there. Where it says regression weight, I'm going to type in 0.22. Now in this case, what's going to happen is it's going to fix this path coefficient to 0.22. And so when the model is estimated, that's one less parameter that's going to be estimated. So I'm going to click through this and rerun it. And so now you'll see, when we click on this button right here, you'll see the 0.22 remains fixed, as does the 1 right here. And so we have essentially 5 parameters that are being estimated instead of 6. So we have the variance here, that's 1, 2, 3, 4, and 5. And so the number of distinct elements in the variance covariance matrix is still 6. So we have 6. The degrees of freedom would be 6 minus the number of parameters that are being estimated, which is 5. So that's going to give us a degrees of freedom of 1. And so that's what you see right here. So now when we look also under our view text, you can see the model fit And so in this particular case, you could actually use the goodness of fit indices to evaluate the fit of the model. And the chi-square value up here with the degrees of freedom, this is another indicator of fit. And we could think about the original model where we estimated all the parameters freely as sort of an unconstrained model, whereas this model we've actually incorporated, we fixed a given parameter, and in that particular case, this chi-square would actually be a test of the difference between the model where there's where that path coefficient is not fixed and the model where it is. And so that would, given that this is statistically significant, that would indicate that we have a significant decrease in fit as a result of imposing that fixed parameter. So at any rate, so just kind of as a comparison between the two models, you'll see, this is the variance, the estimate of the error variance before and after. So you can see the error variance actually got larger. You can see that this is the path coefficient, the freely estimated path B in the initial model versus the current model. So you can see that the values changed. You can also see, basically the variances are exactly the same as is the covariance between the exogenous variables. Also, if we look back at our output and we go to estimates, you can see now that we have path B is still freely estimated, but this is that fixed parameter that we included within the model. And so all the other freely estimated parameters, you can see these are them right here. Okay, so also because I've already said that the model exhibits a poor fit to the data. Now let's try another example where we fix the path coefficient for path A to negative 0.06, which is a little bit more in line with what the original path coefficient estimate was when we were freely estimating that parameter. So I'm going to go back here and right click, go to object properties. Again, you might have to kind of mess around with it a little bit, but I'm going to type in now negative 0.06. So I'm still fixing that path coefficient, meaning that I'm still going to have degrees of freedom of 1, which, if you have degrees of freedom at 0, that means you have a just identified model. If you have degrees of freedom that's greater than 0, then you have an over-identified model. And that's, over-identified models are ones where you can actually go through and evaluate the global fit statistics to evaluate the overall fit of a model. So now I'm going to click on the Calculate Estimates button right here, and you can see there's our degrees of freedom. The chi-square is much lower now, so it actually looks like there's probably a better fit. So if I click on this button right here, you can see that there's our error variance, and it's much more in line with what the original error variance was when we freely estimated this parameter. But again, this parameter right here is still fixed, and so there you go. And so you can see the variances and covariance is exactly the same as before, but this path coefficient right here is changing, reflecting the fact that, again, we've imposed, we've created a fixed parameter for that original path between age and deference. So looking at the fit statistics, we do see that in general they are indicating good fit. The RMSEA, on the other hand, is kind of indicating a poor fit of the model to the data. Now, we could also compare the residual matrices from the three models that we've run. So if we go under and just to kind of show you where to get that, if you click on estimates and go to matrices, I'd asked for, when I ran this, I'd asked for the residual moments. So that's the reason why I can go under estimates and I can find under matrices the residual covariance matrix and the standardized residual covariances. And you can see in this particular case that you see that we have several zeros within the matrix, but this element right here and this element right here are definitely not 0. If I wanted to kind of evaluate for testing whether the residuals are significantly different from 0, I can refer to the standardized residual covariances, And if I want to test at the 0.05 level, what I would be looking for are residual, standardized residual covariances that are greater than, say, 1.96 in absolute value, or or I could have test at 2.58 or whatever. But nevertheless, basically we can see that the relation between age and deference, that there is some indication that we haven't fully accounted for the original sample covariance between those two variables, but this is not, this might not be considered really that bad, and that's why our fit statistics are doing, they look pretty good. You can also see for deference that this is an estimate related to the variance in the difference, or the error variance. So you can see that the estimated error variance, there's not, it's not that different from 0. So just to kind of compare against the original model, though, let's say that I free this parameter. Oops. Go back to this right here again, and I'll just free this. I'll call it path A right here, and re-estimate. And so there's our initial estimates. If I go under estimates right here and under matrices, you can see that all the elements within the residual matrix are 0, and obviously then all the standardized residual covariances are 0 as well. And that's because we've essentially, with our regression model, we fully reproduced the variance covariance matrix. So that's what happens with a just identified model. So within our third model that we just tested, where we set that path coefficient to negative 0.06, we had some minor deviations from this, although the model did okay in terms of fitting the data. If we go back and let's say we want to fix this back at 0.22, so I'm going to fix the path coefficient right here to 0.22, we can see the difference as well. So now when I run it and I go back and we look at the estimates and matrices right here, you can see that much larger values for the residual covariance between age and deference, and you can see for the variance for deference, and you can see that both of these values right here within the standardized residual covariances, both of those are well above the 1.96 that I was referring to earlier. So that's definitely indicating that we're not doing a very good job with this model in reproducing the variance covariance matrix. So another type of parameter, I kind of hinted at it earlier, is called a constraint. And basically what happens in that case is that we constrain the estimation of parameters to a certain set of values. Probably the most common constraint within the context of SEM is an equality constraint, where you are constraining parameters to essentially equality, to have the same value. So just as a couple of demonstrations right here, now what I'm going to do is I'm going to place an equality constraint when I'm estimating path A and B. So what I'm going to do in this case is I'm going to go to Object Properties, and I'm just going to call this path, and for this path right here, I'm going to call it path as well. So when I use the same label, what's going to do is it's going to create an equality constraint. So it's going to force both of these path coefficients to have the same value when they're being estimated. So we are still getting an estimate of these relationships here, but the estimated relation between age and deference and between years and deference is going to be the same. So there's the equality constraint. So I'll click on Close and hit Calculate Estimates right here. And you can see that in this particular case, when I click on this box button right here, you can see that now we have the equality constraint imposed. So both path coefficients are constrained to negative 0.08. So because these path coefficients are constrained to have the same value, then we're still estimating 5 parameters instead of 6 within the model. So the degrees of freedom is still 1, so we still have an over-identified model. And it turns out that the model actually fits the data pretty well. And so if we go under view text and look right here, we can see under estimates, you can see the label path right here, and we have the same estimates, the same obviously standard error, critical ratios, and so forth. So really just one parameter is being estimated, but and essentially applied to both path coefficients. So that is, a demonstration of a constrained a model where we have constrained parameters. If we want to look under matrices and just see what happens there, you can see that these values are much smaller, and within the standardized residual covariance, as you can see, very pretty small values as well. So it actually turns out that the model fit is really not so is really quite good. So there's the chi-squared test. That's non-significant. That's indicating good fit. There's our CFI, TLI. Both of those are indicating very good fit. The RMSEA turns out to be 0. Again, indicating a very good fit of the model to the data. So just as another example, let's say that we want to impose an equality constraint on the variances for our age and years variable. We could do that as well. We'll just go back right here. We'll right click, go to Object Properties, and I'll assign the same name. So I'll just type in VAR here and VAR here. And so now we've got two sets of equality constraints. We're constraining the path coefficients to equality and the variances of these two variables to equality. Just keep in mind, this is completely atheoretical. This generally is not going to make a whole lot of sense in applied SEM settings. But this is just me demonstrating how you can impose equality constraints. So at any rate, I'll run the model, and so now you can see that now we have degrees of freedom set at 2. So we have essentially, we're estimating the error variance here. We're estimating a constrained path coefficient here. We're estimating constrained variances right here, and then we're estimating the covariance right here. So as you can see, the chi-square is 729.2. It's actually a terrible model when you look at it. There's a CFI of 0, and when you scroll down, you can see the RMSEA is like 1.4. Under estimates, if we want to look at the matrices, you can see that considerable model misspecification right here, and so forth. But again, in typical settings, you would not do this, but this is again just to highlight what constrained parameters are. In particular, looking at equality constraints. As I said earlier, you can actually use equality constraints when comparing parameters between groups. So those types of constraints are oftentimes used when you are carrying out multi-group SEM. So that pretty well concludes this discussion.